for the benefit of those who are not able to attend, I am going to share the screen. The agenda for tonight is that we need to finish the discussion of descriptive statistics, missing data, and outliers. We were not able to really take a look at the box plot, which includes the 5-number summary, and then also how to determine if the data set has outliers. I want to remind you that mini project number 1 is due on Sunday, which is January the 29th. And then hopefully we will begin the discussion of random variables, which is actually the lesson we're supposed to be covering tonight. So I have kind of summarized for you in this document, and I will post it with the Zoom recording kind of the material that we talked about last week to lead us back into the discussion of the box plot. And you need that information so you can finish mini project number 1, which we'll get to, and I'll see if you have questions about in a little bit. So last Thursday, excuse me, we we're discussing descriptive statistics and the important characteristics of data. And there are 5 important characteristics of data. You have the center, variation, distribution, outliers, and time. I've added an extra one in here. The measures of center that we talked about were the mean, the median, and the mode. The measure of center is kind of your middle or representative value. It's also sometimes referred to as the average. The mean is the actual average where you add up all the values and divide by the total number you have. The statistical term is mean. It is the most important of the 3 measures of center because it uses all of the data values and is used in other statistical calculations. The median is the middle data value when the data is ranked or ordered. The mode is the one that occurs the most often. Minitab will calculate all 3 of those values for you. Second characteristic is variation, which has to do with how much the data varies or the difference between data values within a data set or within the values of the set itself. So we can compare different data sets or compare a set to itself. There are 3 measurements there as well. You have range, variance, and standard deviation. The range is very easy to calculate. It's the maximum minus the minimum. But if you have outliers, it is affected by those outliers. The variance is an unbiased estimator. It's actually probably the best of the 3, but it is very difficult to interpret because you have square units. The standard deviation is the most important of the 3 most important and useful measure of variation. Again, since it uses all the data value and is used in other statistical calculations, and it is by definition the square root of the variance. Position is not really one of your important characteristics, but it leads us to the distribution and the outliers. So measures of position, which we also talked about last week, are percentiles, which divide the data into 100 equal-sized groups, and each group contains 1% of the data. There's various ways to calculate percentiles depending upon what assumptions you are willing to make about your data set. So we don't actually calculate the percentiles. Quartiles, however, we do calculate using Minitab, and It divides your data into 4 equal size groups with 25% of the data in each group. We ultimately can use the quartiles to help us determine or find the outliers. Within the quartiles, we have the interquartile range, which represents the middle 50% of the data. The key thing to remember is how to interpret the quartiles, and it's the percentage of the data values that fall below the quartile value. Whether it's quartile 1, it's 25%, 50% is quartile 2 or the median, and 75% is quartile 3. Again, we can visualize those quartiles on a box plot, and the box plot includes the 5-number summary, which is the minimum, quartile 1, the median, quartile 3, and the maximum. The third characteristic really is the distribution and thinking about the shape of the graph. Where are all of the data values? Are they clumped on the low end? Are they clumped on the high end or in the middle? And we looked at 3 different distributions, and you can look at them whether you're looking at it on a histogram or looking at a box plot. And I've already drawn the box plot here. So skewed to the right, most of your data falls on the low end, and you have very few on the high end. So in terms of the box plot, the box is near the low end. If you compare your measures of center, the mode is the smallest, then the median, then the mean. The symmetric, most of your data is in the middle. The box on the box plot would kind of be in the middle, and your mean, median, and mode are all approximately the same value. Skewed to the left, most of the data fall on the high end with very few on the low end. The box is near the top or near the high end. The mean is the smallest value, then the median, then the mode. The fourth characteristic is outliers. Outliers are the values that do not seem to fit with the rest of the data. We can get a visual picture of the outliers using the box plot from Minitab, but we can also verify it using the formula that you see there. That is one of the few calculations that you will have to do by hand. It is not something that Minitab will calculate for you. And then the last characteristic is time, and we talked about how that characteristics could change over a period of time. Now, I know that was fast and furious, but we talked about it in detail last week. I want to go through an example, kind of reasonably start to finish, of how to create the histogram, how to determine your descriptive statistics, look at how to create the box plot and do some interpretation of the box plot, and then determining your outliers. Okay, because those last 3 things, the box plot, interpreting your quartiles, and outliers, are things that we did not cover last week, and I know that you have to do it on Mini Project 1. Okay, so I'm using a data set. You don't have this data set, so hopefully you can kind of focus on what we're doing in Minitab, because you could do this on any data set. And the question is, what is the average height in inches of the US president? Okay, so I've already pulled the data set into Minitab. But to remind you, for those of you who were not present last week, there are videos in D2L on how to do it, but you go to File, open, and I'm opening a project from a local file, and I choose the president's physical data. I do continue without autosave, and it brings in my data. I'm interested in the height, which is in column 4. Height is a quantitative continuous variable. It's quantitative because it's a number. It's continuous because I'm measuring, and a person could be half an inch or a quarter of an inch. So it does include smaller units because I'm measuring. That makes it continuous. It is at the ratio level. Technically, if something is 0 inches in height, okay, it doesn't exist. So I know that at the beginning of project 1, you're asked to identify your variable. The variable that I chose from this data set is height. And I specifically chose in inches. And you're asked to determine what type variable it is. And again, it is quantitative continuous at the ratio level. I then want to create a histogram. I want to create a picture, a visual display of that variable. It is a graph. So I go to graph. I want to make a histogram. We keep it as simple as possible. We're only using one variable. The variable I chose is height in inches. And then I click OK. And I get this graph. My horizontal axis is labeled with the height in inches. That was the information that's there. Then we have the frequency on the vertical. The one thing you have to do is you have to update the title. The title should be detailed and descriptive. Who, where, what, when. To do that, click somewhere near the graph and then use this drop down menu, the upside down triangle in the right corner, to change the height. So this is the heights in inches of US presidents. Once I'm done, I can close that window. Remember, I mentioned to you that while you're in Minitab, this is interactive. I can see that the first bar, if I hover my mouse over the first bar, that first bar is in the bin or the group 63.5 to 64.5 with a value of 1. If I go over to the tallest bar, it's between 71.5 and 72.5, and there were 11 values. Now, when I copy this over to Word or Excel or PowerPoint, I'm going to lose that interactivity. But you have to copy it. You have to create a histogram for Mini Project 1 for one of your quantitative variables in the assigned data set. I'm going to copy. Again, I click on the graph. use the drop down triangle and choose copy. And then I go over and I can paste it into my document. You then have to kind of explain what your graph is talking about. Okay. And I may have to toggle back and forth, but this is, we can say this histogram represents the heights in inches of the U.S. presidents. The heights in inches, or the height, I guess I should say heights, in inches range from, and again, if I use the interactivity, I can see this first bar, the lowest value was 63.5. And if I go up to the highest bar, it goes to 76.5. So I would say that they range from 63.5 inches to, I forgot what the other one was, 76.5 inches. It appears the histogram is skewed to the left with more presidents, more left, where more U.S. presidents are taller than, because you have more people or more presidents on the high end than you do the low end. So I've indicated the distribution. We could get an idea, maybe, let's see, what were the other questions that I kind of asked there so I can address them for you. And do I have that pulled up? Let's see. Distribution range, what value appears to be most common? Does there appear to be any extreme outliers? Okay, so looking at my histogram, which one appears to be most common? The most common height would be the one that occurs the most, and that's in that range 71.5 to 72.5. So, you know, if I hit middle of the road, I could say 72 inches. So I might say the most common height of U.S. presidents is between 71.5 and 72.5 inches. Outliers, if I'm looking at this picture, there doesn't really appear to be any kind of gaps. We might, since there's this one here that's between 63.5 to 64.5, and then there's a gap, we might argue, we could say possibly the one U.S. president whose height is between 63.5 and 64.5 inches is an outlier. We haven't verified that. We haven't confirmed that, but it is possible. And again, then you can make any other observations that, you know, that you maybe find unusual or odd. Okay, so you kind of tell what the histogram is telling you. Questions on that piece before I move on? Okay, then the next question you're asked is to create a box plot. Okay, we did not talk about the box plot the other day, on last week. So I want to show you how to create a box plot. The box plot is also a graph. So again, we go to graph and I find the option for a box plot. Pretty common sense. I want to make a graph. The specific graph I want to create is a box plot. We want to keep it simple. Again, we're only doing one variable. Then again, I choose my variable height in inches. I'm going to choose options. I don't need anything there except for the default. And then I click OK. And I get this picture. Okay. Now, again, I have this one changes just a little bit. My scale is now on the vertical. So the height in inches is here on the vertical. If I hover my mouse over the blue box, it tells me that quartile one, the values for quartile 1, the median, quartile 3, and the interquartile range, and that I had 45 values. Okay, so on this box plot, and I want to copy it over to my paper so I can make some marks on it. But before I do that, again, you want to make sure that you give it a descriptive, detailed title. If you leave it as box plot of height in inches, Miss Ralston knows that you didn't change it because that's the default, and I will take points off. It should be a detailed, descriptive title. So this is the height in inches of U.S. presidents. Close the window. Then I'm going to copy the graph. Again, when I copy, I lose some of that interconnectivity. Y'all give me just a second. My daughter is texting me and she doesn't realize I'm in class. Okay, so when you look at this box plot, okay, and Minitab was giving us some numbers, okay, this lower, when you think about this box, this lower, the lower bar of the box, that represents quartile 1. The upper part of the rectangle, the top, is Q3. This line in the middle of the box is your median, which is Q2. So this area on the box plot that's in blue is your interquartile range. That box is around the middle 50%. Interquartile range. Interquartile range is abbreviated IQR. Interquartile range. Interquartile range. Then out from the box, you have these vertical lines. The vertical lines run usually to the minimum and to the maximum, but not always. It varies from picture to picture, but if you're drawing it by hand, it goes out to the minimum and then out to the maximum. In between And what I mentioned to you about the quartiles, between the minimum and quartile 1, you have 25% of your data. Between quartile 1 and quartile 2, you have 25% of the data. Between quartile 2 and quartile 3, you have 25% of the data. And then between quartile 3 and the maximum, you have the final 25%. Now notice visually, those areas don't appear to be the same size. Okay, but remember, our data set appeared to be a little bit lopsided. So, and let me get the numbers over here off of the graph. Again, if I hover over the blue box, I get the numbers. It tells me that quartile 1 is 68.75. The median is 71.5. Q3 is 73. So I've created the box plot. One thing that I do not see on this box plot, if there were outliers, we would see stars or asterisks. Okay, we don't see any. Let me see if I can. I'm going to see if I can make a box plot with some of this data so you can see what I'm talking about. Let's see. Let's do. Okay, I did one for body mass index. See these 3 stars, the little asterisk symbol? If you hover over it, it tells you that that's an outlier symbol. So I can visually see from the box plot whether or not I have outliers. Again, if I hover over it, it even tells me what that value is. Okay. So for body mass index, there appears to be 3 outliers, and there can be outliers on the high end or the low end, or both at the same time. But if you'll notice on our box plot for height, you do not see any stars, which means there are no outliers. So again, what I would do for my mini project 1 is I've got to kind of summarize what it's telling me. Again, think about your what information is displayed, the distribution, your range of values, the middle. Do there appear to be any outliers? And the biggest one that students overlook is interpreting each quartile. And I'm about to show you how to do that. So I hope you're paying attention. Okay, so I might say this box plot represents the heights in inches of the U.S. presidents, the heights in inches range from, again, if I go back to my graph, it tells me that the whiskers, those long lines, go from 64 to 76. So they range from 64 inches to 76 inches. The median or the middle height is what did it say? 71.5 inches. There does not appear to be any outliers. The distribution appears to be, and you could argue, you know, do you think this box is in the center? Do you think it's, you know, further up towards the high or the low? It really should be the same as what you said for the histogram. The histogram we felt, or at least I said, was skewed to the left. So I really should also say that my box plot is skewed to the left, meaning that my box itself is up further on the high end than it is on the low end. All right, and then we need to interpret the quartiles. Okay, here's the interpretation of the quartiles. 25% of the U.S. presidents are shorter than 68.75 inches because Q1 had a value of 68.75. So that means that 25% of the data are below that value. So we're saying it's below Q1. Now I phrased it to fit the idea of heights. 50% of the U.S. presidents are shorter than 71.5 inches. Again, that's below the median, or what we call Q2. 75% of the U.S. presidents are shorter than Q3, which is 73 inches. It's always below, okay, when you do the interpretation, it's the percentage that is below that value. Questions? All right. On the box plot, okay, if you look at the next question, it says calculate using Minitab, label and list the 5-number summary from the box plot, but I also want you to include the mean and the standard deviation. So I'm really asking you here to calculate the descriptive statistics, but I'm really only asking you to calculate 7 of them, okay? I'm really only asking you to calculate 7 of the descriptive statistics. Now, on your homeworks, you may have been asked to calculate more than that, because you could be asked to do the mean, the median, the mode, the range, the standard deviation, the variance, quartile 1, quartile 3, interquartile range. I think that's it. Okay, so you could be asked to do more, but for your project, you need the 5-number summary, which comes from really the box plot, but it's the minimum. You want to give me the minimum, quartile 1, the median, quartile 3, the maximum, and then I ask you to also include the mean and the standard deviation, because those two values are the most important of our descriptive statistics, because they use all of the data values and are used in other statistical calculations. Minitab will calculate all of these for you. Some of them you can get from the box plot, but I would tell you to actually do the calculations. Here's how you do the calculations. We want statistics So we go to stat. These are basic statistics and they're descriptive. So we go stat, basic statistics, display descriptive statistics. Let me do that again. Stat, basic statistics, display descriptive. And then I have to choose the variable. I'm doing height. And then I go to statistics. I need the mean, the standard deviation, first quartile, median, third quartile, minimum, maximum. And I'm going to have it do in non-missing and in missing. I want to remind you how to do that. Now I could calculate any of these here. I could have it do any of them. Okay, but these are the ones that you're asked to do with the inclusion of your totals. I click OK. I click OK again. Guys, there's more to it than simply copying those results over to your paper. You need to actually write them down. Okay, I need to know that you can read this information. You can put it in table form, you can put it in sentence form, but the minimum is 64. Quartile 1 is 68.750. The median is 71.500. I really don't need the zeros. You don't have to add them. Quartile 3 is 73. The maximum is 76. The mean, and let me see if I can scroll this up some. The mean is 70.9 and my standard deviation is 2.785. Now, if you had a question about missing data values, this number N star is the missing data values. For this particular data set, I'm not missing any of the heights for the 45 US presidents. Again, you cannot simply copy the results and paste them. You need to write them out in sentence form, make a table or a chart like I've done here. I need to know that you can read those results. Questions on how to calculate those things?
I do have one question. I already made a submission for the mini project. Are we able to make multiple submissions or?
Yes, you can actually,
Okay.
if you want to delete the one that you submitted first and submit the corrected one, that's fine.
All right. Thank you very much.
Other questions?
I'm sorry, Professor Rosny, can you go back up so I can get a picture of the 75%, that part? Can you go over that one more time? Because I'm still not 100% clear on the 25%, that portion of it.
All right, let me put the numbers in here and that may help you out here. Okay.
Okay, thanks.
Let me change colors. Let's go light blue. Okay, so from mini tab, I know that Q1 is 68.75. Q2 is 71.5 and Q3 is 73. Okay, those are like cutoffs or benchmarks. Okay, between the way quartiles work, if you're thinking about it on a horizontal number line between the minimum and quartile 1, you will always and forever have 25% of the data. So 25% of the US presidents, because that's what I'm talking about in this particular example, are shorter or less than 68.75 inches, because that's the value that has been calculated from the data for Q1. If I go on out to Q2, which is the median, between Q1 and Q2 is an additional 25%. So between the minimum and Q2, you have 25 and 25, which is 50. So when we do the median, we have to say that 50% of the data, in this case, the heights of US presidents, are below 71.5. It's 71.5 because that was the value that was calculated in Minitab for Q2, or for the median. Then we go one more to Q3. Between Q1 and Q3 is the third 25%. And between Q3 and the maximum is the final 25%, because it does have to total to 100. So each region, you divide your data set, all of the data set, 100%, into 4 groups. Each group gets 25%. But then when I'm reading this graph, if I go from, go from the minimum to Q3, I have 1, 2, 3, 25s. 25, 25, and 25 make 75. So I would say 75% of the data, in this case, the heights of US presidents, are below 73 inches, which that was the value for Q3. The key to the interpretation is it's always the percentage below. Deidre?
Okay, I think I got it. Thank you.
You're welcome. Okay, so again, on the 5-number summary, I included how many data values I had, and I had it also indicate how many were missing. For the data set we're looking at, there are none missing. But you could have data sets where there are values missing. So just, again, you read that from this printout at that point. Now, visually, from looking at the box plot and really kind of looking at the histogram, we believe there are not any outliers. But we're basing that on a picture. And while the picture is helpful, we need to verify. We need to prove it with the numbers. Okay, so I have that back up here in the notes. Okay, with outliers, you visually determine whether you have outliers by looking at the box plot and looking for the stars. But we verify that using the formula. And the formula is stated here. I know that it's also included on Mini Project 1. I give you that formula. so that you know, don't have to go look it up somewhere. It's there. Okay. That is one of the few calculations that you are going to have to do by hand. But to do it, I'm missing a piece of information because I need the interquartile range. Okay, so when I get ready to do the outliers, I need quartile 1, I need quartile 3, and I need the interquartile range. All 3 of those numbers in order to plug in or do the calculations. Now, we already have, Minitab has already calculated Q1 to be 68.75. It's already calculated Q3 to be 73. I can find the IQR, but I'm going to have Minitab do it. If I go back to Stat, Basic Statistics, Display Descriptive, and I go back to my stats and I tell it I want the interquartile range, I'm also going to go ahead and get the mode because I'm going to need it in a minute. The interquartile range is 4.25. 4.25. Okay, so the formula says any data value less than Q1 minus 1.5 times the IQR. Make that bigger. Or greater than Q3 plus 1.5 times the IQR. Okay. Do not overthink this. This is a flat out plug and chug. You have the formula. You have the numbers. We're just going to plug them in. So for the first one, I would have 68.75 minus 1.5 times 4.25. Now, guys, you got to follow order of operations, which means you do the multiplication first. So 1.5 times 4.25 gives me 68.75 minus 6.375. Then I do the subtraction and I get 62.375. Then I'm going to do the other calculation. Q3, which is 73, plus 1.5 times 4.25, multiply first, 73 plus 6.375 gives me 79.375. So basically what we're saying is if there is any president that is less than 62.375 inches or greater than 79.375 inches, then they would be considered an outlier. It would be unusual for the U.S. president to be shorter than 62.375 inches or taller than 79.375. Go back up here and look. The minimum value we had was 64. I don't have a number less than 62.375. The maximum was 76. I don't have a number bigger than 79.375. So I have confirmed without a doubt that there are no outliers. Okay, visually we saw that there are no outliers. I have confirmed no outliers because no U.S. president height is less than 62.375 inches or greater than 79.375 inches. I proved it. Questions? The last thing that we need to do, that you're asked to do on the project, and that you really need to do anytime you're looking at it, visually, using our eyes, we've said we believe the distribution is skewed to the left. I want to prove it, verify it, confirm it with the numbers, because my eyeballs could be seeing something different than your eyeballs. For that, remember, we compare the mean, the median, and the mode. If it is really skewed left, then the mean should be less than the median, which is less than the mode. So if I look at my numbers, let's see, we had a median of 71.5. Okay, so the median was 71.5. The mean was 70.9. And I need to go back to Minitab to get the mode. The mode was 72, and it occurred 6 times. There were 6 presidents who were 72 inches tall. So the mode is 72. Well, look at there. 70.9 is less than 71.5, and 71.5 is less than the mode. I have verified with the numbers that this distribution is skewed left. And I'm done. That finishes the discussion of descriptive statistics, missing data, and outliers. And you should have all of the information necessary to finish or do mini project 1. Mini project 1 is due Sunday. Now, do you have any last minute lingering questions related to mini project 5? Again, please let me stress. Please, please, please follow the instructions. Okay? I ask you more than once to use detailed, complete sentences. I also ask you very clearly at the beginning to identify the data set you're using. There is a specific data set for those of you who are in healthcare management. There is a different data set for those of you in logistics and supply chain. but I don't know which one you are. Okay. I can't tell by your name whether you're healthcare management or logistics. Please identify the data set, and it really should be throughout business 3000. I have a typo. Any questions before we move on? Okay, I'm going to save these notes and I will post them with the recording so that if you want or need to go back to them, you can. I am going to utilize the PowerPoint that's available in D2L for the next lesson. The next set of lessons is related to it's called random variables, but the topic really is probability distributions. They're connected together. You would have talked or should have learned about some of these probability distributions in Stat 1401. So again, hopefully some, but not all of this content in this lesson is a review as well. Okay, everything we've done up to this point really should have been a review of the content from Stat 1401. Some, but not all of this will be review as well. So we're going to start with kind of an overview of what is a probability distribution and why do we need them. So we just kind of finished talking a little bit about the graphs, but we know that we can also take data and organize it into a table form. And the fancy term for that table in statistics is called a frequency distribution. And that table or that frequency distribution all can give me kind of a jump start to know what type of graph I may want to create and that sort of thing. But the key thing about the frequency distribution, or even the graphs that we create, the histogram and the box plot that we were just looking at, those things show what really happened or what actually happened. They are the reality. But everything, we don't necessarily always have or know what actually happened or what is actually going to happen. So we also have a probability distribution. The probability distribution describes what probably, what could happen based on an assigned probability for every possible outcome. Think about flipping a coin. Well, I kind of know if I'm going to flip a coin. Let me see if I can make some notes. If I'm going to flip a coin, I know that when I flip a coin, I'm either going to flip a head or I'm going to flip a tail. And I can, from what I've learned through the years, through experience, that kind of thing, I know that the probability of a head is 1 out of 2. There's one way to get a head out of the 2 options that I have, which is also, if you want it as a percentage, 50%, or as a decimal is 0.5. Same thing with a tail. There's 1 out of 2 ways to get a tail, which is a 50% chance or a 0.5 chance. So we know what happened. We got a 50-50 chance of flipping a head if I flip the coin one time. But what if I flip it 10 times or 20 times or 100 times? What's the probability that I would get, you know, 5 heads or 20 heads or whatever? So we assign a probability to a particular outcome, and then we can create a theoretical model to predict what is going to happen. And those probability distributions can be written or displayed as a table, as a graph, or even a formula. I Googled right before class, I Googled to see if I could find some examples of using probability or probability distributions. I mean, obviously, we think about probability within weather forecasting. And typically with anything associated with betting, whether it's sports betting, playing the lottery, playing cards, that kind of thing. But then think about politics. Political forecasters use probability and probability distributions to predict the chance that a certain candidate is going to win the election. Sales forecasting, if you're in business, a lot of companies will use probability and create a probability distribution to determine the chance that they'll sell a certain amount of items on a given day or a given week or a given month. Again, that helps to predict inventory. Even health insurance rates, car insurance rates, life insurance rates are determined based on the probability that you're going to life insurance, the probability that you're going to live the next year for another year, or for health insurance, how likely you are to spend a particular amount on health care in a particular year. Again, they may look at factors like your age, existing medical conditions, your current health status, to determine the probability that you're going to spend $10,000. Or with car insurance, they may look at your age, your past driving experience, or are you a brand new driver? My daughter just recently, well, about 6 months ago, turned 15, so we had to add her to our insurance. And so her insurance rate is different because she's a young driver, that kind of thing. Grocery store staffing. They use probability to determine how many workers they should schedule on a given day. Do they have more customers come in, on Friday, Saturday, Sunday, or do they have more come in, middle of the week on Wednesday? Again, to get an idea of how many customers are coming into the store. Natural disasters. They determine how likely it is that, a hurricane is going to hit a particular area, or a tornado, or an earthquake is going to strike at a particular time in a particular area. Again, looking at traffic patterns. Okay, so there's lots of uses. Investing, that's another one related to business. So there's lots of uses for probability distributions. And again, it's more of a theoretical model than the reality. The frequency distributions that we've talked about previously are our reality. Our probability models are, kind of the pie in the sky. This is what we think should or could happen. This just kind of gives you a picture of how that particular process works. And I just showed you that there's lots of decisions made in business, insurance, and real life by assigning probabilities to a particular outcome and then evaluating those. So we're going to talk about two different types of probability distributions. The first type is called a discrete probability distribution. Couple of things about discrete probability distributions. If you think about discrete numbers, data that is quantitative discrete, we noted was countable. We were counting and it was whole units. So a discrete probability distribution has a countable number of possible outcomes. I'm going to flip my coin 10 times. So I'm going to have 10 outcomes, 10 things that could happen. The probabilities can be determined theoretically or by observation. Sometimes if we don't know about something, we can actually do research, and then based on the research and the patterns that we see, we can develop a probability for a particular event. Again, we can show or display the discrete probability distribution in a table form or as a graph. The two key things to remember, which are really direct results of probability theory, is that the probability of each outcome must be between or equal to 0 and 1. Okay, all probabilities are between 0 and 1. And just for review's sake, let me go over to my piece of paper and make you a few notes about that. And I keep losing my pen. Okay, so all probabilities are between 0 and 1 inclusive. So if you think about that like a number line, probability of 0 means the event is impossible. I had my brain froze for a minute. Okay, probability of 0 means the event is impossible. It is not going to occur. No way, no how, no matter what you do, that event is not going to occur. For example, if I say, what's the probability that you roll a 7 on a die? Now, die is a 6-sided cube and it's numbered 1 to 6. There is no way you would ever roll a 7. If I say, what's the probability that Thanksgiving is on a Sunday? Well, if you know anything about the calendar within the United States, Thanksgiving is never, ever on a Sunday. It's always on a Thursday. So there's no way that Thanksgiving is going to be on a Sunday. On the other extreme, you have 1. A probability of 1 means that it is certain it's going to occur regardless of what you do to try to prevent it. It's going to happen regardless. Again, thinking about examples, if I say, what's the probability you roll a number less than 7 on a die? That's 100% or 1, because every number on the die is less than 7. So regardless of what I roll, I'm going to get a number less than 7. Probability Easter is on a Sunday. Well, there again, if you're familiar with the calendar within the United States, Easter is always on a Sunday. So there's a 100% chance it's going to be on a Sunday. And then you can have any value between 0 and 1. It can be a decimal, it can be a fraction, or it can be a percentage. So probabilities can be decimals, fractions, or percentages. So if you think about, the halfway point would be 1/2 or 50%. And we tend to think about this, think about it like a thermometer. If you're close to 0, your event is less likely, or it's unlikely. But as you move towards 1 and the values get higher, the event is more likely, or we just say likely. So if I have a probability that's kind of close to 0, we tend to think that that's very unlikely. It's less likely. If it's between about 0.5 and 1, or the closer I am to 1, the more likely the event is to occur. Again, we think about it like a thermometer. The closer you are to one end or the other. If you get middle of the road, you're kind of, you could go either way. Okay, so all probabilities are between 0 and 1 every time, all the time. The other requirement is that the sum of the probabilities in what's called the sample space are equal to 1. If you consider everything that can happen for that particular event, your probabilities must add to 1. Again, let me give you an example. Let's use that easy example we were looking at just a minute ago. If we use the idea that we're going to flip a coin, and we know when we flip a coin that we could get a head or we could get a tail. And we know that the probability of getting a head is 1 out of 2 or 50%. We know that getting a tail is 1 out of 2 or 50%. That's the only two things that can happen when I flip a coin. If I add those two things together, 1/2 plus 1/2 is 1/2, or 50% and 50% is 100%. So if I consider all the things that can happen, then the probability has to total to 1. Those two rules, guys, are going to be super important as we move forward. For the other type of probability distribution is called a continuous probability distribution. And again, it's the idea that we're on a continuum, usually something associated with measuring, so that you don't have any gaps in the number line. You have an infinite number of outcomes between any two given values. Again, you're kind of on that interval. You can break it down into smaller and smaller units, and you don't have any holes or gaps in that measuring instrument. Typically, with a continuous probability distribution, the probabilities are determined theoretically. Again, we can display them in the form of a table or a graph. I will tell you that in most cases for discrete, you see them in table form, and for continuous, you see graphs. Now, they can be either, but again, you tend to see discrete as tables and continuous as graphs. The two requirements for a continuous probability distribution are really the same as we had for discrete, but they're worded differently. Okay, the idea that the probability has to be between 0 and 1, let me get down here where I can make, has the same idea when we say the probability of each outcome is between or equal to 0 and 1. And then the sum of the probabilities being equal to 1 is the same as the total area under the curve. Again, because visually for a continuous probability distribution, more times than not, you're going to see a graph. And so you're looking at a curve or some sort of graph. And again, the total area under that graph is supposed to be 1. We'll talk more about that when we get to the continuous probability distributions and talk about them in great detail, which will most likely be next Thursday. Last thing here is I mentioned we're going to talk about those two different types. There's lots of them. For our purposes, we're going to talk about kind of a generic discrete probability distribution here in module 1, and we're going to talk about the binomial. A couple of other discrete probability distributions are Poisson and hypergeometric. I will tell you that if you are really interested in statistics, or if you're going into a field where you need a strong background in statistics, you can actually take an entire course on probability distributions. So remember, for our purposes, we're skimming the surface. We're going to talk about two of the more commonly used ones. Similarly, with continuous probability distributions, we're going to talk about the uniform distribution, the exponential distribution, the normal distribution, the student's t-distribution, chi-square, and the f distribution. And you can see there the modules in which we'll be doing that. Okay, so we're going to shift our focus now to discrete probability distributions, and specifically to the general, kind of the generic, that kind of one size fits all deal, discrete probability distributions. Any questions before I do that? Okay, again, I'm utilizing the PowerPoint that's available in D2L, and we're going to focus our attention on discrete probability distributions. By the end of this lesson, hopefully you can recognize and understand discrete probability distribution functions in general. You want to be able to determine if a given scenario represents a discrete probability distribution, and to calculate the mean and the standard deviation of that discrete probability distribution. You want to be able to calculate and interpret expected values. And then also we're going to do the same thing with a binomial probability distribution. I don't know. I hope we can get through both tonight, but I don't know if we will. Okay, so discrete probability distribution, again, as I just said, have a countable number of possible outcomes. They're displayed on a table or a graph, more likely a table. The probabilities are determined theoretically or by observation. And then you have the two requirements that we just discussed in great detail. For the generic discrete probability distribution, there are formulas for the mean and the standard deviation. Okay, so you may want to go to a separate piece of paper and begin to make you a list of the formulas. So you may want to go like to a clean sheet of paper and maybe label it probability distributions. And then label it general. And we're going to have a formula for the mean, and we're going to have a formula for the standard deviation. This is one of the few that Minitab is not going to do for you. Okay, you will have to do this yourself. Okay, so these are really hand calculator type questions. Okay. So you may want to begin to make yourself a formula sheet to have next to you when you are working on the homeworks. You'll be able to kind of create a note sheet for the midterm. So you want to start making a list. So the mean is, these are the formulas, mu equals the sum of x times p of x. Basically, you're going to take each value, each outcome, and multiply it times its probability, and then you're going to add them up. That's what that formula says. It says take each x value times its probability, and then add those results. Mu is the same symbol for the mean that we had for the descriptive statistics, so that symbol hasn't changed. Okay, so the formula for, and if you need to, when you're writing your formulas down, make yourself a note about what that means. But the formula here is the mean is each x times its probability, and then you add them up. This big funky looking E symbol, let me change my color. This big funky looking E is the Greek letter, it's Greek uppercase actually, uppercase letter sigma. And in mathematics, not just in statistics, in mathematics, whenever you see that symbol, it means total or add the values that are indicated. And it's telling you to take each individual x and multiply it times the probability of x. For the standard deviation, the formula looks a little wonky, so hang on. The standard deviation is the square root of the sum of x minus the mean squared times the probability of x. Okay, so this one's a little bit different. You have to subtract the mean that you just calculated from each x, square it, multiply the answer times the probability, and then add the values up. Okay, I'm following order of operations. I take each individual outcome, subtract the mean, square it, multiply it times its probability, and then add them up, and finally take the square root. Now we're going to do this in a minute, but you kind of need the formulas beforehand. So again, when you write your formula down, you may want to make yourself some notes. So it's the standard deviation is the square root of the sum of each x minus the mean squared times the probability. So we're going to take a look at some examples similar to the questions that you might see on your homeworks, on your midterm related to discrete probability distributions. And again, this particular question, if you want to make a note of it, is kind of a general discrete probability distribution. Now, the first thing we need to do is to decide, first of all, is it a discrete probability distribution? So to make that decision, we need to check two things. Okay, we need to confirm that all of the probabilities are between 0 and 1. So if I look down this second column of values, that's labeled P of X. That stands for the probability of my variable. I have 0.08, 0.16, 0.32, 0.28, 0.12, 0.04. All of those numbers are between 0 and 1 on the number line. None of them are negative, and none of them are over 1. So I can say, get back up there. Whoops. Check. Okay. I can check off that yes, I have verified that. And let me have to go back through here just a second. Okay, so remember this is general. First thing we did was we confirmed that all the probabilities are between 0 and 1. Check. The second thing we have to verify is that the probabilities add to 1. So I would need to look at this list of numbers and I'm going to add them together. Now you can use your calculator. Okay, I'm going to do it in my head so you can see what I'm doing. 8 plus 6 is 14, plus 2 is 16, plus 8 is 24, plus 2 is 26, plus 4 is 30. So I have 0, carry the 3. 3 plus 1 is 4, plus 3 is 7, plus 2 is 9, plus 1 is 10. So 0, carry the 1. 1 plus all those zeros is 1. Bring my decimal point down. It does total to 1. Now, guys, you can do the same thing punching it in your calculator. 0.08 plus 0.16 plus 0.32 plus 0.28 plus 0.12 plus 0.04. It comes out to be exactly 1. So I can say check. Yes, this is, or this table does represent a discrete probability distribution. Now, it gives me the scenario here of what that represents. It says a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. The X represents the number of times that a patient rings the nurse during a 12-hour shift. Then the possible outcomes, they could ring it 0 times, 1 time, 2 times, 3 times, 4 times, 5 times. We have verified that it is a discrete probability distribution. Okay. Let's look at another one. This one says a company wants to evaluate its attrition rate. In other words, how long new hires stay with the company. Over the years, through observation, they have established the following probability distribution, where X is the number of years a new hire will stay. They stay 0 years, 1 year, 2 years, 3 years, 4 years, 5 years, 6 years. So P of X is the probability that the new hire will stay with the company X years. Okay, so let's look at this table. Again, if we want to verify that this is a probability distribution, the first thing that I notice is I have some missing information. I don't know what the probability is for 4 years. But what I do know is that all probabilities have to be between 0 and 1, and the probabilities have to add to 1. So I know if I were to total up these probabilities, it would have to equal to 1. If I know that, can I figure out what that empty blank should be? I hope you realize that I can, because what I can do is, if I know that has to total to 1, and it does, if I subtract the value for 0, the value for 1, well, I guess I better not put the parentheses in there. You guys won't like that. If I subtract the value for 0 years, subtract the value for 1 year, subtract the value for 2 years, subtract the value for 3, subtract the value for 5, and subtract the value for 6, whatever's left has to be the value for 4, because it's got a total to 1. So I've got 1 minus 0.12 minus 0.18 minus 0.3 minus 0.15 minus 0.1 minus 0.05, and it comes out to be 0.1. So again, if I'm looking at this, I can now see that all of my probabilities are between 0 and 1, and now it totals to 1. I can also ask you some questions related to that particular table. For example, the first question here says, find the probability that X equals 4. Well, that's what we just did. That was the missing piece. Then it says, find the probability that X is greater than or equal to 5. You have to really pay attention to these symbols. Okay, so we're saying, what's the probability that a new hire is going to stay 5 years or more? So in this case, in this scenario, that would be that they stay 5 years or 6 years. You include the 5 because it has the equal. So I'm going to add those two probabilities together. For 5 years, it was 0.10. For 6 years, it's 0.05, which means, adding that together, there is a 0.15 or a 15% chance that a new hire is going to stay 5 or more years. I am calculating the probability of a particular event using the information in the table. Be extra careful. Read the values. Be extra careful reading the values. The next one says, what's the probability X is less than 4? What's the probability that a new hire stays less than 4? So less than 4 could be 0 or 1 or 2 or 3. I do not include the 4 because it says less than 4. One thing I'll remind you about probability in case you don't recall, typically when you think about the word or implies you're going to add, because I'm going to add together 0, which is 0.12, plus 1, which is 0.18, plus 2, which is 0.30, plus 3, which is 0.15. Now I'm going to use my calculator. 0.12 plus 0.18 plus 0.3 plus 0.15 is 0.75. There's about a 75% chance that a new hire will stay less than 4 years. I'm simply reading the information from the table and performing the indicated calculations. You have to be extra careful and pay attention to the symbols. Okay, this is the same problem. Okay, I just carried it over from the other page, I think. Nope. Is it? No, it's a different problem. Okay, this goes back to the first one about the researcher. Okay, so this question is about the researcher. I've got the wrong numbers in there, but anyways, on average, how long would you expect a new hire to stay with the company? I've got the wrong table in there. Okay, let me see if I can fix that real quick. I can't fix it. So we'll just go with the numbers that we've got. Okay, so it says on average. Okay, average, remember, is a synonym for the mean. So they're really asking me, what is the mean for this data set? Okay, or for this probability distribution. Well, the formula for the mean, remember, is I'm going to take each X, multiply it times its probability, and then add them up. I'm going to write this out so you can see what I'm doing. I would take 0 times 0.08, that's its probability, plus 1 times 0.16, plus 2 times 0.32, plus 3 times 0.28, plus 4 times 0.12, plus 5 times 0.04. You take each X and multiply it times its probability. It might even be helpful if you make yourself a table and make yourself a column of each X times its probability. Okay, so I would have 0, 0.16, 0.64, let's see, what's 3 times 0.28, 0.84, 4 times 0.12 is 0.48, and 5 times 0.04 is 0.2. Okay, so I take each X, multiply it times the probability, get the answer. And then I'm going to add those answers together. So I have 0 plus 0.16 plus 0.64 plus 0.84 plus 0.48 plus 0.2, which gives me 2.32. So the mean of my data set is 2.32. Then to get my standard deviation, which is the next question, again, it might be helpful, and let me see if I can get this table, if this to let me copy this table. I'm going to bring it over here to my paper, hopefully. Okay, so that it might be easier if I make myself a table so that I have the X, okay, which is 0, 1, 2, 3, 4, 5. And then to do the standard deviation, I need X minus the mean. And then I need X minus that mean squared. And eventually I'm going to do X minus the mean squared times the probability of X. It may help me if I set it up in table form. Well, the mean was 2.32, so I've got to do 0 minus 2.32, which gives me negative 2.32. 1 minus 2.32 is going to be negative 1.32. 2 minus 2.32 is going to be negative 0.32. 3 minus 2.32, get my calculator, is 0.68. 4 minus 2.32 is 1.68. And 5 minus 2.32 is 2.68. So I do the subtraction. I take each X, subtract the mean that we just calculated. And then I've got to take each of those numbers, those answers, and square it. So I would have negative 2.32 squared. That's 5.3824. Negative 1.32 squared is 1.7424. Negative 0.32 squared is 0.1024. 0.68 squared is 0.4624. 1.68 squared. Just takes a long time to do it, but you gotta do it. I suppose if you're good with Excel, you might could set you up an Excel spreadsheet to do it for you. And then 2.68 squared equals 7.1824. And then I have to take each one of those numbers and multiply it times the corresponding probability. Okay, so I would have 5 0.3824 times 0. Oh, wait, 0.8. Sorry, looked at the wrong column. No, no, no. 0.08, 1.7424 times 0.16, 0.1024 times 0.32, 0.4624 times 0.28, 2.8224 times 0.12, and 7.1824 times 0.04. Now you got to do each one of those individually, or I'm going to add them as I go. Okay, I'm going to enter into my calculator 5.3824 times 0.08 plus 1.7424 times 0.16 plus 0.1024 times 0.32 plus 0.4624 times 0.28 plus 2.8224 times 0.12 plus 7.1824 times 0.04. Okay, I've done the multiplying and the adding at the same time, so that when I get down here, I have a total of 1.4976. And the last step to get my final answer is to take the square root of that number. And the square root of that number is approximately 1.22376, and so forth. Usually you're asked to round to 2 places. That would round to 1.22. It's not necessarily difficult. It does take a little bit of time. Okay, it does take a little bit of time, but it's not supposed to be difficult. Okay, so my standard deviation ultimately is 1.22. Again, thinking about the problem, you know that the probabilities have to total to 1. So here I have 35, 50, 60. So the probability of 4 years would have to be the 0.40. Again, because your probabilities must total to 1. So the probability that it takes 4 years to complete the BBA degree is 0.04 or 40%. Then you have probability it takes more than 5, which would be the probability of 6 or the probability of 7. Again, the word or mathematically implies to add. So you would add those two probabilities together. This is just an additional example that I have here on the PowerPoint. Less than 5, less than or equal to 5 in this scenario would be 3 or 4 or 5. Again, or implies the addition. So you would have 0.05 plus 0.40 plus 0.30. So there's about 75% chance that it's going to take less than or equal to 5 years to complete it. Now I think the next one's another find the average, okay? And I don't have time to go through that again. And I'm not going to get to the binomial, okay? So here's the plan. And I'll make the adjustment pretty much right after we're finished. We have finished descriptive statistics, missing data, and outliers. Your mini project number 1 is due on Sunday. At this point, that is the only thing that you have due this weekend. I did not get through random variables far enough for you to do the homework. Okay, so the only assignment you have due this weekend is your mini project 1. We did not finish random variables. We will pick back up with discrete probability distributions, specifically with the binomial, next Thursday, and then continue that discussion with the continuous probability distributions, specifically the uniform and the exponential. I have about 7 minutes left. Do you have any questions that you may want to ask related to mini project 1? Okay, if you don't, then we will adjourn for the evening and we will pick this discussion back up next Thursday.
Thank you very much.
You're very welcome. I'll see you guys later.